on open interval a b, and then there is at least one point, but before that the derivative of the g function should not be 0 in any point on the open interval, and what we conclude is f b minus f a upon g b minus g a equals to f dash c upon g dash c. I will discuss the proof of this theorem on the board. For this purpose, I may start with this function phi of x is, it is f x minus f a minus f b minus f a upon g b minus g a into g of x minus g of a. So, we may start with this function. Now, as per the conditions of the Cauchy's mean value theorem, my function f, it is continuous on closed interval a b, differentiable on open interval a b. My function g x, this is also continuous on closed interval a b, differentiable on open interval a b, and therefore, my function phi of x is continuous on closed interval a b and differentiable on open interval a b. So, it satisfies two conditions. Now, I will find out phi of a. Phi of a, it is when you put x is a, this is 0, when you put x is a here, this is 0. So, phi of a is 0, and when you put x equals to b, this would be f of b minus f of a, this is g b minus g a, that will cancel. So, what we find is that is also 0. So, what we get is phi of a is 0, phi of b is 0. It means that my phi satisfies all three conditions of Rolle's theorem. It is continuous on closed interval a b, differentiable on open interval a b, and phi of a is phi of b, and therefore, I may apply Rolle's theorem to this new function phi, and therefore, there exists at least one point C on the open interval a b such that phi dash c is 0. Now, let us find out the derivative of phi. Phi dash x, it is derivative of f of a is constant, hence the derivative is 0, f b minus f a upon g b minus g a into derivative of g, and therefore, phi dash c is, it is f dash c minus f b minus f a upon g b minus g a into g dash c. But as my function phi satisfies all the conditions of the Rolle's theorem, I can use the conclusion of the Rolle's theorem, that is phi dash c is 0. So, 0 equals to f dash c f b minus f a upon g b minus g a into g dash c, and therefore, this f dash c equals to, it is f b minus f a upon Gb minus Ga into G dash C. So, finally, what we find is Fb minus Fa upon Gb minus Ga equals to F dash C upon G dash C, and this is the conclusion of the Cauchy's mean value theorem. So, if we have even two functions f and g, and if these two functions satisfies both the conditions that f is continuous on closed interval a b, g is continuous on closed interval a b, and both the functions are differentiable on open interval a b, and if the derivative of g is non-zero for every x in open interval a b, then f b minus f a upon g b minus g a is f dash c upon g dash c. Now, we will see the geometrical meaning and the other applications of the Cauchy's mean value theorem in the next slide. Before that, let me remark that this Cauchy's mean value theorem is the generalization of the Lagrange's mean value theorem. If we put g x is x in this theorem, we will get the Lagrange's mean value theorem. Next slide. Geometrical meaning of the Cauchy's mean value theorem. Here we may begin with the independent variable t on the closed interval a b, and we will put x is g of t and x is f of y is f of t, and if we plot the graph of y against x, we get the continuous curve from point G A F A to point G B F B, and will join the chord A B, and therefore, the slope of this A B, it is F B minus F A upon G B minus G A, and by Cauchy's mean value theorem, this equals to F dash C upon G dash C, that is nothing but the slope of the tangent to the curve at the point C, and here the F dash C upon G dash C is nothing but the derivative of y with respect to x at point C. So, we must get at least one point on the curve at which the slope of the chord joining A and B, that equals to the slope of the tangent, and here in the figure we will see this, that there is a point C at which the tangent is parallel to chord A B. Now, we will see one or two examples of the Cauchy's mean value theorem. If we are given a function f x equals to e raised to x and g x equals to e raised to minus x. So, now I have a function f x equals to e raised to x and g of x is e raised to minus x, and my interval is the closed interval a b. Now, we will verify the conclusion as well as the hypothesis of the Cauchy's mean value theorem. For the hypothesis, both are the exponential functions, very standard functions, they are continuous as well as differentiable. So, both the functions they satisfies the hypothesis of the Cauchy's mean value theorem, and therefore, there must be at least one C belongs to A B for which it satisfies the conclusion, that is F B minus F A upon G B minus G A equals to F dash C upon G dash C. So, now we will put the values and we may find the number C. So, this is e raised to b minus e raised to a, and this it is e raised to minus b minus e raised to minus a, and the derivative of e raised to x, it is e raised to x only. So, this is e raised to c, and the derivative of e raised to minus x would be minus e raised to minus x. So, this is minus e raised to minus c, and this is e raised to b minus e raised to a. Here if you take the LCM, then you will find e raised to a minus e raised to b upon e raised to a into e raised to b minus e raised to c upon 1 upon e raised to c. Here if you take minus sign common, and here it is already minus sign. So, this will cancel, and what we find is e raised to a into e raised to b equals to e raised to 2 c, and therefore, it is e raised to a plus b is e raised to 2 c, and therefore, a plus b is 2 c. So, c equals to a plus b by 2, and this a plus b by 2, it is definitely between a and b, that can be checked easily. A is less than b. So, if you add a plus a is less than a plus b. So, 2 a is less than a plus b. So, a is less than a plus b by 2, and if you add b, a plus b is less than b plus b. So, a plus b is less than 2 b, and therefore, a plus b by 2 is less than b. So, this my number a plus b by 2, it is definitely between a and b. So, this justifies the conclusion also that I can get a number c between a b, at which I have the condition f b minus f a upon g b minus g a is f dash c upon g dash c. So, this was the one application of the Cauchy's mean value theorem. I will show you another example also. Let me have that slide, so I can write the inequality. So, in the previous slide I have this inequality, that for number between 0 and 1, I can prove this 1 minus x upon 1 plus x is less than log 1 plus x upon it is sin inverse x. So, now I will prove this inequality on the board. And for that purpose, from the observation what we require is, I may start with one function as f, another is g. So, let me have the function f x, it is log 1 plus x, and my x is positive. So, I can consider the interval 0 to 1, and the another function it is g x, it is sin inverse x. I will use the same interval for the another function also. So, now both these functions are continuous, differentiable, and if you find the derivative of g, that is 1 upon root of 1 minus x square, and which is not 0 for every x in the open interval 0 1. This is 0 if you put a, this is not defined even if x is 1, and for other values you can check with inequality also, that is this is non-zero number. So, now I have all three conditions, it is continuous, differentiable, and the derivative is non-zero, and therefore, by the conclusion of the Cauchy's mean value theorem, there exists at least one C in the interval 0 1 such that this f 1 minus f 0 upon g 1 minus g 0 equals to f dash c upon g dash c. Now, f 1 is this, it is log 2, or let me have this interval 0 to x, that would be fine. So, it is f x minus f 0 upon g x minus g 0. So, this is log 1 plus x and f of 0 is log 1, which is 0, and sin inverse 0 is also 0. So, this is sin inverse x. F dash c is derivative of log, that is 1 upon 1 plus c at c. This it is root of 1 minus c square. So, what we find is this, it is log 1 plus x upon sin inverse x. This equals to, it would be root of 1 minus c upon 1 plus c. On simplifying, we will get it. Now, because of the time constraint, I am not developing that inequality, but already my previous speaker Ramesh bhai show how to develop the inequality using this. So, using the condition on C, that your C belongs to this 0 x, one may derive this inequality, and one can prove that this value, the value is always between 0 and 1. This can be proved, and then using this number 1, we may conclude that, this can be proved between 1 minus x upon 1 plus x to 1, and then the value of this is nothing but it is root of 1 minus x upon 1 plus x is less than log 1 plus x upon sin inverse x